All right, in lesson 3 of compensating wage differentials, we're going to model the compensating wage differential that is paid to seasonal workers using a neoclassical model, the one that we've been, using all semester long. The simple one, the Cobb-Douglas function, where utility is the square root of consumption times leisure, right? In my model, the wage rate is $20.80. And this varies from student to student, but the 4,000 hours, the endowment of time that each worker has each year is going to be held constant across all of us, right? So for all of us, the worker can devote up to 4,000 hours to work and leisure each year, right? And generally speaking, the more consumption one gets or has or can afford, the more utility that person will receive. The more leisure that person gets, the more utility that person will get, right? Now, when consumption increases, utility or worker satisfaction increases, but at a decreasing rate. And we can see that over here. If I hold leisure constant at, say, 100, you can see in the graph here that utility is rising, but at a decreasing rate. And that's the law of diminishing marginal utility, right? You can say the same thing about if we hold consumption constant and allow leisure to rise, right? So as leisure increases, utility increases, but at a decreasing rate, right? Again, that's the law of diminishing marginal utility. That's what's really cool about this type of utility function. It models that law, right? So now if I want to solve this, if I solve this for C, right? If I solve this for C here, then I can get and I hold utility constant. If I solve this for C, holding utility constant, I'll get what is what's called the indifference curve, right? And so in order to do that, you have to square both sides of the equation, right? When you square both sides of the equation, what happens to the square root of something? If C times L were 100, right? Because C is 10 and L is 10, right? If C times L is 100, then that blue thing would be 100, right? And the square root of 100 would be 10. And the square of 10 would be 100, right? So when you square a square root, you get whatever's under the root, right? Now, what I want to do is I want to move the C times L to the left and the U squared to the right. Which I did here, right? Now, I want to divide both sides. I want to divide both sides by L. So I'm going to divide this side by L, and I'm going to divide this side by L. Okay, when I divide both sides by L, I can cancel the L's. I don't like the word cancel. I like L divided by L equals 1. So when L divided by L, right? When we do L divided by L, we get 1, right? And 1 times C is C. This is the indifference curve. Once I know what U equals, right, I can draw an indifference curve. So this right here, this curve that bends toward the origin, that's the indifference curve. At this point here, utility is 9,000. At this point here, utility is 9,000. At this point here, utility is 9,000 or 10,000, 9,000. At this point here, utility is 9,000. So anywhere along this curve, worker satisfaction is held constant, right? And what's happening to leisure? Leisure is 2,000, and as leisure goes up, the second number, consumption, is going, as leisure increases, consumption is decreasing, right? You see that? So that's our indifference curve, right? If we hold utility constant. So our indifference curve is C equal to U squared divided by L, right? And that produces this curve here, right? Produces this curve here. And that utility, the utility level here on this black curve is about what? Well, with leisure about 2250, looks like consumption is about 37,000, right? So what is the utility level here? Consumption is about 37,000. And leisure is 2250, right? So if leisure is 2250 and consumption is about 37,500, then the utility on this curve is somewhere around 9,100, right? Okay. Now, this right here is the slope. This is the equation for the slope of this curve, right? If we hold consumption constant and we increase leisure, what happens to the slope? It goes down, right? As the denominator gets bigger, if we hold that constant, the slope gets smaller. But along the difference curve, like I illustrated over on the right, when I go down an indifference curve, consumption is falling and leisure is rising. So as consumption falls here, leisure is increasing. A falling variable, a variable that decreased because another variable increased, that results in a smaller slope, right? Well, how did I come up with this equation? Well, let me go ahead and delete these. So here's my utility function. Here's my indifference curve holding that utility constant, right? I'm going to differentiate this equation with respect to L. When I differentiate this equation with respect to L, it makes it easier if I move the L up into the numerator. In order to move the L up into the numerator, I have to make the exponent -1, right? Now I can get rid of the fraction. So that's the first thing I want to do, right? The next thing I want to do to differentiate this with respect to L, right? I want to put a D in front of C. So this means differentiate C with respect to L, right? So I want to differentiate the thing in parentheses here. I want to differentiate the thing in parentheses here with respect to L. Now I can write it like this too, right? This means differentiate this with respect to L. Now, if I put the C up here, this implies there's a change in a difference in C over a difference in L. In calculus, this difference in L is infinitesimally small, right? In economics, we always think of the change here as a 1-unit change. So from 2,000 hours of leisure to 2,001 hours of leisure, right? We always think of that as a 1-unit change. In calculus, it's an infinitesimally small change, something not equal to 0, but really close to 0, right? And then this would be the resulting change in, for example, consumption here, right? So one thing we need to recognize here is U squared is just some number, right? U squared is just some number we've plugged in. And U squared can be, say, 100, right? If I change this part, if I change the L in this part, if I increase the L, L to the minus 1 will go down, right? But that has no effect on this part, right? So U squared is a constant. So what you want to do here is you want to factor out the constants, right? And U squared is constant. It's going to stay the same by assumption, no matter how much we change L. So I'm going to move it outside. Okay. Now I'm going to copy this and place it down here. Okay. Now, when we differentiate something that is raised to an exponent, right? I'm changing L a little bit, right? When I change L a little bit, when I differentiate this function here with respect to L, the way you differentiate is you subtract 1 from the old exponent, right? And the old exponent is minus 1. So the new exponent becomes minus 2, right? The new exponent becomes minus 2 because we're doing minus 1 from minus 1, right? We're subtracting 1 from a negative 1. So that becomes negative 2. We also want to multiply by the old exponent. So we're going to pull out the old exponent here. We're pulling out the old exponent, right? Now, this right here is, that right there is this. So we can delete the DL here. We can delete this part, right? So this right here, these two things are that, right? Okay, cool. Now we can simplify. I'm going to rewrite this. We're going to simplify some stuff. So L to the minus 1, that's L to the minus 2. And I'm going to multiply that by U squared, right? Then a minus 1 times this, well, that just makes the whole thing negative, right? So I'm going to delete this part. Okay. The next thing I'm going to do is I'm going to move the L to the minus 2 down back into the denominator, right? I want to put this back in the denominator. And how do I do that? Well, I was going to do L squared, right? Now I'm just moving this into the denominator by making the exponent positive, right? Okay, the next thing I want to do, right? The next thing I want to do here is I want to replace U with what it equals. What does U equal? U equals the square root of C times L, right? Now I got the square root. This right here is U, right? That right there is U. What is the square of a square root? Well, before we said what? The square of a square root is what? It's just whatever's under the root symbol, right? If this stuff in blue is 4, the square root of 4 is 2. 2 squared is 4, right? So the square of a square root is just whatever's under the root symbol, and that is C times L, right? Now I can do one last cancellation here. I can do one last cancellation. L divided by L squared, well, that's just L, right? So this right here, I'm going to move this down. This right here is the slope. This is the formula for the slope of this curve, right? And we call that slope the MRS. Call that slope the MRS. And it is negative, right? It's negative because it's downward sloping. The indifference curve is downward sloping, so the slope is negative, right? So this means the indifference curve is downward sloping. And this just means as we increase consumption, right? As consumption decreases, L has to increase in order to keep utility constant. So we're holding utility constant here. What's happened to the slope? Well, consumption's fallen and leisure's increasing, and the slope is getting closer to 0, right? So if that fell and that increased, right, then the slope would be close to 0 or closer to 0, right? So that's how we got this equation here. So I'm going to go ahead and I'm going to delete all this stuff here, right? So we're going to have the utility function. We're going to have the indifference curve that holds utility constant. And then we're going to have the slope of the indifference curve that is holding utility constant, right? Okay. So that's my utility function. That's my indifference curve. And this is the slope of that indifference curve, correct? Okay. Now we want to create the budget line. The intercept of our budget line, remember W is just some number we assumed, right? In my case, 20.8. T is a number we assumed. In everybody's case, it's 4,000. So the W times T is the intercept of this budget line. So what is W times T? In my case, it's 20.8 times 4,000. So my intercept is 83,200. Now, what does that mean? If we don't leisure at all during a given year, and we devote all of our time, this 4,000, which is basically 2 full-time jobs. This is 80 hours a week for a year, right? With a 2-week vacation. That's what this 4,000 represents, right? So if we work 80 hours a week for 50 weeks out of 52 weeks for the year, we have a 2-week vacation, right? And we work a total of 4,000 hours, right? We can earn $83,200 at a wage of $20.80, right? So that's what that means right there. And then this is just the wage rate. The wage rate is $20.80, right? Now, when I hit enter, that produces this budget line here, right? And we have the familiar optimal solution, right? The 1 point, this indifference curve touches this budget line at one and only 1 point, this dot. And we label it O for original optimal solution, right? At the original optimal solution, leisure is 2,000, right? In my model, leisure is 2,000. That means hours worked is 2,000 because 2,000 plus 2,000 equals this 4,000, right? And then consumption is, looks like it's between 37,500 and 50,000. One way to find it is to multiply this 2,000 here by $20.80, right? So if I multiply this 2,000 hours, if I multiply the 2,000 hours of leisure by the wage rate, and I subtract that from the 83,200, I get a consumption level of 41,600. So this right here, this height is 41,600, which makes sense because it's closer to 3,750 or 37,500 than it's, than 50,000, right? Okay, so this consumption level is 41,600. That's how we would find that, right? Now, at the optimal level of consumption and leisure, 0.0, the worker chooses 2,000 hours, whatever that is in your model. In my model, this worker chooses 2,000 hours of leisure, right? And I plug it into my budget line here, right? And so this is the wage, right? Right here. And this is our time constraint, right? So my consumption level is 41,600. All right. Now, if you don't have a 2,000 here, you might have something else. If you have something else other than 2,000, it's kind of hard to do 4,000 minus like 1960, right? So I'm going to do is I'm going to write my time constraint here, 40,000. That's how much time I have to devote for leisure or work. I'm going to subtract off my leisure, right? And that leaves me 2,000 hours to devote to work, right? So my arithmetic is much easier than probably yours, right? It just so happens that hours worked and leisure are equal to the same thing, right? In my model. And what is the utility here? So my leisure is 2,000, right? So I'm going to copy this up here. My leisure is 2,000. my consumption level is $41,600, right? $41,600. So my utility, to how many decimal places? To 2 decimal places. So my utility level is, I'm going to copy that. My utility level is 9,121 and 4/10, right? Or 40 hundredths, right? And this is in units of utility, whatever that is, right? Whatever that is. Now, using the MRS equation near the top of the problem, my MRS is C divided by L, right? So C divided by L. Okay, using the MRS equation near the top of this problem, the worker's marginal rate of substitution is equal to what? Well, in order to calculate the marginal rate of substitution, you have to do the consumption level divided by the leisure level, right? So I'm going to just copy this right here. Copy. And then I'm going to change the multiplication to division, right? Whoops. So I have 41,600 is the consumption level, and the leisure level is 20,000 or 2,000, right? And then my marginal rate of substitution is negative. So it's a negative of what? The wage rate, right? That's the wage rate. Now that is not a coincidence, right? That is not a coincidence. Why? Because at this optimal solution, right, this curve is just tangent to that line. And if I zoom in on this point, right, if I zoom in on this optimal solution here, you can see that the indifference curve here, when I zoom in on it right here, the indifference curve looks like the budget line, and both have the same slope, right? Both would have the same slope. So the slope of the indifference curve at the optimal solution is the same as the slope of the budget line, which is negative 20.8. So it is not a coincidence that the absolute value of this MRS is equal to workers' hourly wage rate of $20.80, right? The MRS implies that the worker at point O here, point O, let me shrink that down a little bit. There you go. Okay, the MRS implies that the worker at point O, right here, is willing to give up what? Remember, economists interpret the slope as what? We interpret this change. Remember this right here, the MRS. We can change MRS with DC DL, right? And when we differentiated this utility, this indifference curve with respect to L, in calculus, we would interpret this change in L as really, really tiny. The number closest to zero without being zero, right? Really tiny. And this would be the resulting change in C, right? But in economics, we interpret this change in L as 1, right? So if L increases by 1, what does consumption change by, right? And it just so happens, right, that our MRS was the absolute value of it, right, was 20.8. So we're just looking at the absolute value of it, right? So ignore this part over here. So this is the MRS here, right? The MRS is the change in consumption along an indifference curve that corresponds to a change in leisure, right? And we said it's equal to 20.8. Well, you can't, when you have two components of something, the change in consumption or the change in L, it's hard to interpret just the number. So what we're going to do is we're going to change this to 20.8 divided by L, right? Or divided by 1, right? And what we can do is we can make that negative right? We can make that negative. We can make this negative. We can make this positive, right? So the MRS, as we said, is a negative 20.8 here, right? And the MRS is defined to be the change in consumption holding utility constant at whatever it is, divided by the change, some really small change in leisure, right? And that we said it was equal to 20.8. Well, it's hard to interpret a number when you have two components, right? The change in consumption or the change in leisure. So we put this negative 20.8 in the numerator of a fraction with plus 1 in the denominator. Why? Because negative 20.8 divided by plus 1 is still negative 20.8, right? So this is a little easier to interpret. So if we increase leisure by 1, what happens to consumption at our optimal solution? Well, if we increase leisure by 1, right, we're going to drop consumption by $20.80, right? So that's what this is saying here. The MRS implies that the worker at point 0 is willing to give up $20.80 in consumer goods, right? $20.8 in consumer goods to get an additional hour of leisure. So this is the additional hour of leisure, right? And this is the drop in consumption. And we're holding utility constant at what? Whatever this was, right? We're holding utility constant at whatever it was. 2 decimal places, it's 0.4, right? In my case. As you move down along the indifference curve, utility does what? What does utility do? Utility is remaining constant, right? That's why we call it an indifference curve. We're indifferent between a point here. We're indifferent between this bundle of leisure and consumption. Consumption is quite high and leisure is quite small. We're indifferent between this point and that point. Both points gives us the same utility. We're indifferent between this point and that point. Here we have low consumption and high leisure, right? Here we have high consumption and low leisure. Here we have medium consumption and medium leisure. All three of these points on this indifference curve yield the same level of utility, which is why we're indifferent, right? So as we move down this indifference curve, right, utility is remaining constant. So it's either this one or it's that one, right? It's either this one or that one. Now, as we move down this indifference curve, right? As we move down the indifference curve, utility's being held constant. What is happening to the slope of this curve? It's getting closer and closer to 0, right? When we're up here, this curve is very steep, right? As we come down it, it gets closer and closer and closer to 0, right? The absolute value of the slope declines, right? So which one is appropriate? Utility remains constant, and the marginal rate of substitution gets increasingly negative, or the marginal rate of substitution gets closer to 0. MRS is the slope of the indifference curve, right? That's getting closer to 0. Okay. At the optimal point, the worker's wage rate equals remember, sorry, I had to add an answer box there. Remember the wage rate was initially what? $20.80. Right. Let's press enter there. Okay, so at this original optimal solution, the wage rate is $20.80. That's just to remind you of what it is, right? Now, this is the worker. This is the non-seasonal worker, right? The non-seasonal worker is working full-time, right? Around 2,000 hours per year at the normal market wage. Now, this could be a cook at a restaurant that doesn't work at a ski lodge in the mountains, right? This worker is working 2,000 hours roughly a year, right? Around 2,000 hours a year at the market wage of a chef or a cook, which is $20.80, right? Now, suppose you're a ski resort and you're only busy during the winter from, like, say, October through I don't know, end of February, maybe middle of March. You're only busy that time, and you only need cooks part year. Are you going to be able to, if you pay the $20.80 per hour, or whatever your wage is, to them, are you going to be able to encourage people to take a cooking position at your ski lodge? Probably not, right? Because this $20.80 is based on working full-time year round, right? And earning $41,600, right? So now we're going to model what an employer at a ski lodge would do, right? Where the work is seasonal. The worker is contemplating a seasonal position requiring only 700 hours. Now, your hours might be different than mine, right? But keep that in mind, mine is 700. Explain why the worker will not accept the position if it pays $20.80, right, per hour. At 700 hours of labor supplied and a wage rate of $20.80, the worker can purchase how many dollars worth of goods? So let's go back up to here. So we're going to get rid of the 2,000, and I'm going to replace it with the value here in my problem, which is 700. Okay, so, whoops. Okay, hang on a second. All right. So, sorry. Let's reset that. If hours worked is 700, if hours worked is 700, and we have 4,000 to devote to leisure or work, then we leisure 3,300, right? So if I replace this with 3,300, I get a consumption level of 14,560, right? That's not very much, is it? Maybe a more intuitive way to calculate that number would be to do this, right? I take the wage rate times the number of hours the person's working per year, right, in a seasonal job. And I get the same number, correct? See that? So if I work only 700 hours a year at that wage rate, I'm only making 14,560, right? And again, the leisure here, if hours worked is 700, the leisure is 3,300, right? Okay, so that 700 hours is right here, right? So this value here is 4,000. 4,000 minus 3,300 is 700. So from here to there, my hours worked is 700, right? And my leisure is 3,300. So that puts me on this point N here, right? And my consumption level is only 14,560, right? My consumption level is only 14,560, right? So my leisure is 3,300, right? Now that combination of leisure and consumption yields the worker only how many units of utility? So I'm going to change this. I'm going to change this to 14,560, right? That's the consumption level. My leisure level is 3,300, right? My leisure level is 3,300. That means my utility, right? That means my utility is that value. I'm going to copy that over to here. Has my utility fallen? Yes, right? My utility's fallen a lot. Again, I need to round this, right? I need to round that to 3 decimal places. So this 666 becomes 667, right? Okay. So my utility has fallen quite a bit. It's fallen about 3,000, well, about 2,000 units from 9,100 down to 6,900, right? So about 1,200 units it's fallen, right? So the person's much worse off here. And if you draw an indifference curve through point N, it'll look like this, right? It'll start here and then it'll pass through the budget line twice, right? It'll pass through the budget line twice. It'll be parallel to the black one, right? but it'll pass through the budget line twice. Okay. And in the lower indifference curve, right? The indifference curve that's closer to the origin, it represents lower levels of utility, right? Using the MRS equation near the top of this problem, the worker's marginal rate of substitution at this point equals what? Well, we got to calculate the marginal rate of substitution here, right? We got to calculate the marginal rate of substitution. If remember, the marginal rate of substitution is equal to C divided by L, right? So what's my new consumption level? My new consumption level, right? Let me close this out. My new consumption level is 14,560. And my new leisure level, leisure is 3,300, right? All right. So if I divide the consumption level by the leisure value, right? The new consumption level, if I divide the new consumption level by the leisure level, my new consumption level is that, my new leisure level is that, I only get a marginal rate of substitution equal to 4.41, right? A negative 4.41. Now, this marginal rate of substitution implies the worker is willing to give up what? Well, the marginal rate of substitution now at point N is what? It's equal to negative 4.41, right? The marginal rate of substitution is two parts. The change in consumption for some change in leisure, right? So instead of trying to interpret one number with two components, right? One number with two components here, I'm going to put the negative 4.41 in a fraction, right? Negative 4.41 over a positive 1, right? So this says our leisure is going up by 1, our consumption's fallen by 4.41, right? So this implies the worker is willing to give up an hour of leisure for 4.41 more dollars in consumption. So if that's the case, I got to change this to negative and this to a positive, right? A positive 4.41 divided by a negative 1 is the value of our marginal rate of substitution at that point, right? So this says give up an hour of leisure to get 4.41 more units of consumer goods holding utility constant, right? And we're holding utility constant at this value we calculated earlier, right? We're holding utility constant along this indifference curve, right? You gotta realize there's a new indifference curve here, right? And it passes through point N, and then it passes through some point up here, right? Okay, substituting consumption for leisure along the budget line continues until leisure equals what? So in order to maximize utility, right? Here utility is low. So what we do is we give up leisure until we get to what? Until we get to point O here, right? And then at point O, our utility is maximized. At every point between this point and point N, at every point between O and N, you can draw an indifference curve, right? And that indifference curve is going to be closer to the origin, representing fewer units of utility, right? So here we only have 6,931.67 units of utility, right? As we reduce our leisure along the budget line, we're getting more consumption. Our utility is growing, right? Our utility is growing until we get to point O. And then our utility is maximized, right? If we continue up the budget line, now we're getting more and more consumption. We're still getting more and more consumption, but less and less leisure. But now we're below that indifference curve, right? And our utility continues to fall as we go up this budget line, right? So substituting consumption for leisure along the budget line continues until leisure equals what? Well, that was 2,000 hours, right? In my model, utilities maximized at 2,000 hours of leisure in my model, right? And consumption equals what? What was consumption equal to here? It was, between 37,500 and 5,000. I have it at 41,600, right? This point yields what? This point O, right? Point O yields more utility than point N. Point O yielded that much utility, right? That was point O utility. And this is point N utility. And the difference is 2,189.73, right? Okay, so more. So it's got to be this one, this one, this one, or that one. Which one's the closest? This one here, right? 2189. So the worker will accept the seasonal position if the employer offers a high enough wage, right? How high is that wage got to be? We're going to use the model to figure that out, right? Now, models don't work like they do in the real world, right? In the real world, you probably just keep increasing the wage until you attracted a certain number of applications, and then you'd pick the best one, right, for that particular wage. So people kind of discover it with trial and error in the real world. But in economics, we can model this, right? So we're going to use this model to compute the compensating wage differential that makes the worker indifferent between the worker's current employer and the seasonal position. So going back to our graph here, where is that? So what we want to do is we want to find a point on the indifference curve, right? We want to find a point on the indifference curve that makes the worker indifferent between working for the firm, full-time at a restaurant in town versus working part-time at a remote ski lodge, right? So what we have to do is we have to plug this amount of leisure, 3,300, into our indifference curve, right? We have to plug it into the indifference curve. And then once we do that, we can find the consumption level, right? And it looks like the consumption level is going to be about 25,000, right? So about 25,000 in my model corresponds to about 3,300 units of 3,300 hours of leisure, right? So that's what I'm guessing, right around $25,000 in consumption, right? So with only 700 hours available in the seasonal position, the worker will accept the position if the income from this position is at least what? Well, let's go back to our indifference curve, the first one, right? Here's our indifference curve, right? That's our indifference curve. And our utility was what? So when leisure's 2,000, right here, and consumption is 41,600, right? We can find out what the consumption level is, correct? We can find out what the consumption level is. Now, the leisure is 3,300 for the seasonal position, right? That corresponds to 700 hours of work, right? Because 3,300 plus 700 is 4,000, right? So I'm going to plug in 3,300 here. And I get a consumption level of 25,212, okay? So when we round to zero decimal places, we get 25,212, which is right about what I thought it was, right? It was roughly 25,000, right? See that? It's just above the 25,000 mark. And I labeled this point F, which is equal to our consumption if we assume no savings, right? Earnings and consumption are the same thing. If this person earns just above $25,000 in my model, then that person is going to be indifferent between this blue point F and it's black point O, right? At point F and point O, the utility is 9,121, right? So that hasn't changed. The leisure level is 3,300 in my model, right? And so for the person to be indifferent between point O and F, right? At point F, they're working 7 hours a season, right? Per year, because it's seasonal. They have 3,300 hours of leisure. For them to be indifferent between point F and O, they have to make just over $25,000, right? And they're doing that. They're making $25,212 per year, right? So with this level of consumption and that level of leisure, utility is the same as it was at point O, which makes them indifferent between working 2,000 hours a year in a seasonal position or in a full-time position versus 700 hours in a seasonal position, right? Now, remember at O here, at point O, the slope of the indifference curve was equal to the wage rate, because the wage rate is the slope of the budget line, right? To find the wage rate that will make workers indifferent between F and O, what we need to do is we need to increase the wage rate, right? Here, the wage rate is $20.80. That's the slope of this line. What we need to do is we need to create a new budget line that goes from point P here to point F, right? We need to rotate this budget line. And the slope of that line is going to be steeper, right? So in order to do that, we have to calculate the slope of point F to point P, right? To find the slope of the new budget line, which is going to be blue, compute the changes in consumption and in leisure from point F to point P. Then take the ratio of these changes, right? So point P is what we call the endowment point, right? That's an endowment point. This person does not get an allowance, right? So the allowance is 0, right? Because the height of point P is 0. An allowance could be like a trust fund payment per year, right? Where and it doesn't matter how many hours a year you work, you get that same amount every year. It could be a government pension. It could be a military pension. It could be money given to you by your parents, right? It could be a government benefit, some kind of subsidy that does not depend on earnings at all, right? But in this particular model, the allowance is 0, right? This person's endowed with 4,000 hours, right? Which can be devoted toward work or consumption, right? So at point P, right? At point P here, total hours available for leisure is 4,000. At point F, leisure is 3,300, right? So the run here is 700, right? 4,000 minus 3,300, right? So what I'm going to do down here is I'm going to create, this is going to be the slope, right? And we call the slope the economic rate of substitution. So the run is 4,000 minus 3,300, right? Because my leisure at point F is 3,300, right? I think everybody has 4,000 here, but whatever you have here is going to be the leisure at this final point, right? Now at 3,300, what's the height? At 3,300, the height is whatever this was, right? 25,000 something. It was 25,212, right? So minus. Now at 4,000, what was the height? At 4,000, the height is 0, right? So at 4,000, my consumption is 0. At 3,300 hours at 4,000 hours of leisure, I'm not working. I have 0 money, right? At 3,300 hours of leisure, At the new wage that I want to compute, it would be 25,212, right? So let's find out what this is. Let's find out what the economic rate of substitution is on this new budget line. And it looks like it's $36.02 per hour. The slope of this line is $36.02, right? And so the compensating wage differential, my final wage, right? My final wage is $36.02, right? My initial wage was what? My initial wage is $20.80. And so the compensating wage differential is $15.22 per hour, right? If I'm the employer at the ski lodge and I only need 700 hours per season, if I pay them $36.02, I can draw cooks who would have done it for $20.80 year round. I can draw them to the ski lodge by paying them $36.02 per hour. An employer that raises the market wage of a full-time cook from $20.80, increases it by $15.22. They can hire those cooks away from full-time work into seasonal work.